Me and Professor Tian He, who is my supervisor, and we're from the University of Minnesota, Twin Cities. Good morning, good afternoon, or good night, ladies and gentlemen. Based on where you are from, it's my honor to present our work BitLight today. BitLight is a project that uses DLP projectors to achieve the functionality of a virtual touchscreen. Our project is motivated by the idea that can we actually hide tracking data in a light medium while not affecting the perceived content. A very typical use case that you can think about is to use a light sensor enabled gloves, and basically use it as a virtual mouse. The light sensors will be able to receive and decode signals from the projector and figure out its location on the screen. And our project is basically based on the idea that human eyes is actually, in plain words, a very slow camera that is only capable of perceive up to 10 to 12 images per second. Hence, higher rates are not perceived. So, a very simple and naive approach is to basically just embed light changes in every 2 consecutive frames. And that's actually one of the biggest category in the existing literature. The existing literature can be largely categorized into 2. The first category, as I was mentioning just now, use what we call frame-level data embedding, which basically embeds an opposite and complementary signal in every 2 consecutive frames. And specifically, it can be through alpha channels, pixel luminance, or even using a modified color, which means a color that is different but still pretty close to the original color. A pretty big drawback of this approach is such that each frame is only able to encode 1 bit because it's either 1 or 0. Our approach, BitLight, is the first system that is able to embed multiple bits per frame. And we're using a DLP projector to achieve that. So DLP projector has the capability of dividing every frame time into subslots. In the most common scenario, each frame is going to be 1/60 seconds, and we can subdivide that into 24 slots. And for each one of that time slot, we can either turn on or turn off one of the 3 primary color light sources. So quick question is, how many total colors can we generate with the dividing factor of k equals to 24? So that's actually 9 times 9 times 9. Because, for example, in each frame, in terms of the shades of the red light, it can be either 0, 1, 2, all the way until 8. So that's 9 possibilities. So the basic design of our system is such that for the same color, we actually have different possible bit sequencing that all represent the same color. Because the human eyes doesn't really care about the exact sequence of your bit sequence. It only cares about how many turn-on bits are there. So a very natural observation is that actually different colors have a different capability of data embedding. And apparently the color 4G, 4R, 4B is the most powerful in terms of carrying and embedding signal. And on the receiver end, it's pretty simple. If it receives a 1 turn-on bit, it sees some signal. If it's a 0 bit, there's no signal. Okay, so that wraps up the basic design. So we also came up with a more advanced design of further speed up localization. And that's based on the intuition that human eyes actually also has a pretty limited spatial resolution. And nowadays, monitors or projectors can support up to 4K resolutions pretty easily. So we could actually exchange some color bits between and nearby pixels. And we call this local bit exchange technique. So this technique basically is an optimization problem, which has an objective function in mind, which is the average localization speed. And the intuition in solving this problem is such that we diversify the colors on each frame, such that the color distribution are ideally more proportionate to their data carrying capability. And please refer to the paper for more details. We also implemented a system using a 60 frames per second projector, and we evaluated using 12 different video claims with different video and color characteristics, such as fast slow motion, high and low contrast, etc. And pretty understandably, the visual quality increases with high resolution and also decreases with projector distance. And the visual quality degradation also doesn't vary too much across the 12 different videos. And understandably, the larger the number of nearby pixels you merge together, the higher sacrifice or trade-off in terms of picture qualities that you're getting. And our accuracy is up to 2.1 millimeters, which is pretty good. And the average speed of our system is almost 20 times faster compared with frame-level techniques. Even the worst-case speed of our system is, as you can see, almost 25 times faster. And our system is also pretty scalable at higher resolutions based on our simulation results. And mathematically, the localization speed actually follows a logarithmic time complexity with respect to resolution. Okay, so that wraps up my presentation today. We are actually a pretty new system paradigm, and we are a new technique using bit-level color encoding. Thank you.